So the first thing we're going to do is we are going to try to formulate a little cheat sheet, because we did a lot of stuff in the past two classes and we still have a couple of things to finish, right? So let's see if we could formulate some sort of a cheat sheet to summarize everything. Yeah? So let's call this our cheat sheet for vectors. Cheat sheet. And with vectors, well, I might probably want to put the first couple of things on the cheat sheet to be the triangle law. And I will put the triangle law like this, and you notice the arrows there. Remember, the point of the cheat sheet is to just summarize or put it in any way that you want to put. And then I have the parallelogram law like that, or I could form a parallelogram and then I'll get the resultant like that, right? And then on the cheat sheet I could just put you know, A, B plus B, C is equal to, remember the B's kind of cancel off, you could kind of think about it like that. So that gives us A, C. So this is one of the things that I could put on my cheat sheet, and as you can see, I pretty much summarized the triangle law and the parallelogram law in one little line there, right? So let's take this and drag it downwards, and I'll put it over here, and we could see here that we basically did some questions when it comes to finding the resultant using the triangle law. And this is one of those questions that it was a little bit tough, but we could see that it wasn't really anything special. We just applied our same triangle law, but we just had to do it a whole other way around as well, right? Then we spoke about the parallelogram law, and we talked about the resultant with the horse and carriage and such. And then we spoke about negative vectors. So maybe I could put negative vectors on my cheat sheet. Ooh, my cheat sheet turned blue for some reason. So let me turn it back red. And let's add negative vectors. How could I add it? I could say A, B, and we could see here that if I take vector A and I add vector B in this direction, I will get vector C going so, right? The problem is vector B is coming back in this direction. So what I could say is A plus negative B is equal to vector C, and therefore A minus B is equal to C. So this is what I was talking about here, Shizzy, where you use your triangle rule to determine how you're going to add the vectors, but then when you determine how, it's just a matter of plugging in those coordinates and doing it with normal vector algebra, right? So we have here negative vectors, we have parallelogram law, and we have other stuff. Let's see what else. I'll cut that from there. And so we talked about this, and I don't really need this on my cheat sheet. I think that it's pretty okay in terms of you know, knowing how the x's and the y's operate. Like if I have a negative x, I'm moving in this way, and if I have a negative y, I'm moving down. So all of these different vectors here and how they look, you are supposed to be able to just look at two numbers and kind of imagine where that vector would be. And then we looked at the translation of a vector, right? So maybe I could put this on my cheat sheet. And how would I put this? I don't know. So how would I put this on my cheat sheet? Vector as a translation. Well, we could see here that we could add the point A to the vector, and we will get the point, we will get the other point, right? So vector as a translation is we have a point A, And then we have a vector that is moving the point A to point B. And the question is, A, where is point B? What is point B? So we could see here that that what we would do is we could just take point A and add it to the vector, because the vector just tells us how this x and y, how it's going to move. The x is going to move by 4 spaces, and the y is going to move by also 4 spaces, right? So so once we add them, so maybe a vector as a translation, maybe we could do it like this. Translate A to B, right? And then I could put A plus vector P, and I think that the vector just have the line underneath, right? Or is it the line on top? I can't remember. And that gives us B, right? Is the line underneath? Yes. So so we can see here that this is just a little, you know, I just put in something in my cheat sheet here that I will be able to look at and just kind of remember. When I look at this, it'll remind me of this question, it'll remind me of this diagram. And that is what the cheat sheet is all about, right? And the whole reason why we want to have a cheat sheet is when it comes time to revise the topic of vectors, we have everything in one place, right? So let's see what else. So we talked about a vector as a translation, and we actually did a couple of questions there, right? And then we spoke about things like the modulus of a vector, and yes, these little formulas here could definitely go on my cheat sheet, right? So this is the kind of stuff that I want to put on my cheat sheet, little formulas like this. So the modulus of AB, the vector AB, is equal to the square root of, you could say, if vector AB, you could let's just write AB. You know what? I'll write it over. Alright, let's put the vector AB is equal to xy. Therefore, the modulus of AB is equal to the square root of x squared plus y squared. Right? So that is the modulus thing, right? And let's see what else we have to do in terms of vectors. And I'll just probably put this one. Right? So we have modulus, then we have equal vectors. Now equal vectors is super important. It might seem like, oh well, yeah, I mean if they're looking the same, yeah, they're equal, sure. But remember, equal vectors is the whole reason why the parallelogram law works. When I have a resultant come in here and I say, well, you know what, if I complete a parallelogram, this vector is actually equal to this one, and this vector is actually equal to this one. So equal, the concept of equal vectors is the whole reason why the parallelogram law does work, right? So I'm not going to put equal vectors on my cheat sheet, but it is a very important thing. So we might want to just keep a little bit of you know, a memory on that one, right? Definitely a scalar quantity, right? I could definitely put scalar quantity or multiplying by a scalar quantity, right? And the thing is that multiplying by a scalar quantity have directly to do with parallel vectors. And I know how to multiply by a scalar. You just take the 2 and multiply it by the x. You take the 2, multiply it by the y, and you end up with 8, 8. That is all. Right? So I'm not going to put scalar quantity per se, but I am going to put parallel vectors. And I'm just going to put a little symbol like that. Parallel vectors. Right? And parallel vectors could be a scalar quantity. So vector A is equal to the scalar quantity times vector B. So in order to show that two, and this is a super important one, you see the equal vectors and parallel vectors, those guys just always come, right? So So with parallel vectors now, I could just say, well, two vectors are parallel with that. I just need to write that. I don't really need to write anything else. And once I could prove they are scalar quantity, I don't need to write the example. This will help me to remember the example, right? So you all see, I hope that you are learning how to write a cheat sheet. You don't have to write down everything. You could just write something that will remind you of the example that you have in the book, you know, and then you could always, if you forget, you could always go and check out the example in the book. Then we were speaking about vector algebra, and vector algebra is just adding the x's and adding the y's and essentially doing a scalar multiplication if necessary, right? Now this is what Csec was asking about. What is the difference between vector algebra and the triangle law? At the end of the day, you could see here that we are using vector algebra to solve, well, we're using the triangle law and vector algebra together, right? So the triangle law helps us decide what vectors do we add, or maybe we have to subtract, I don't know, right? So it helps us decide what vectors we add or subtracting, and then we do that using algebra, right? So I don't need to put vector algebra on my cheat sheet, but position vectors are important. I do have a couple of little points here that I'd like on my cheat sheet. So on the cheat sheet, I'll put here position vectors. And they're always from the origin. So remember the point A. Let's say the point A is 2, 4. That's just a point, right? And if I have my thing here, 2 on the x, 4 on the y, this is the point A, 2, 4. It's just a point. But if I draw from the origin the line going to the point, that now becomes the vector OA, which is the vector 2, 4, like this, where the origin is moved 4 spaces and then 2 spaces up. So position vectors are like that. So I could just put, if the point A is 2, 4, therefore OA, which is the origin, O, once you see O or origin, you're dealing with a position vector, is 2, 4, right? And then I'll put the, well, I don't need to put the modulus here, because I already have modulus on the cheat sheet. So I'll just put the tan of theta is equal to y, or I don't even need to put that. I could skip straight to theta is equal, and I'll just put here, this is x and y, so that this next one will make sense. The tan inverse of y over x. Right? So my cheat sheet almost done, and as you can see, I just basically taken all the entire topic and I just boiling it down like Baji into one little paragraph, right? Then we're talking about displacement vectors, and we see here it don't really have anything to put on my cheat sheet here for displacement vectors. Because displacement vectors is just a matter of the triangle law, right? At the end of the day, they'll give you a point P and they'll give you a point Q, and they'll tell you to find the vector that will take you from P to Q, right? And what you have to know is, well, if I have the point P, that is a position vector OP, and if I have the point Q, that is the position vector OQ. And now if I want PQ, I could go PO plus OQ, right? And then I'll get PQ, right? So at the end of the day, all I have, remember, all they gave you was 2 points, eh? They just gave you 2 points, right? And you're supposed to know, well, all right, those 2 points could be represented as position vectors. And because is PO plus OQ will give you PQ. Remember, I don't have PO, I have OP. So PO will be minus OP plus OQ, right? Which is PQ. And therefore, I'll end up having OQ minus OP, which is PQ, right? Because it's going in the opposite direction. And then you employ your vector algebra to solve that, right? So I see here there isn't really anything when it comes to displacement vectors. There isn't really anything for me to add to my cheat sheet, because this is just a combination of vector algebra, a combination of position vectors and triangle law, right? And essentially, you know, I have nothing new to add. I just have to know how to do my triangle law. I just have to know how to do my position vectors, and then that is it, right? So now we have here, and this is where we actually stopped last week. And we stopped here last week. So look, I almost have the entire vectors here, you know. And what I could do on my cheat sheet is I could just put displacement vectors, just to remind myself, hey, remember I have that topic, you know. Even though that topic, you know, I ain't gonna put no details about it, but I'll just to remember, hey, that exists. So, you know, so keep your brain on it, right? This next one here is also using position vectors, but you can see this one here, you know, we had the P and we had the Q, and they told us that the vectors OP and the vectors OQ, find the resultant of OP and OQ, right? The resultant OR, yeah? So find the resultant OR, which would be this. And we didn't know how long to draw it. Right? You don't know how long to draw that. The only way you could know how long to draw that is by completing your parallelogram. This has to be equal to this side, and this has to be equal to the other side. And only then will you get this point here, and now you could draw the resultant. Right? So this here again is nothing for me to add to my cheat sheet, but this is, right? We only have these two here to do today. That's it, and then we'll just do some questions. So we have here unit vectors, and this is actually a new thing that we're gonna take on today. Right? And unit vectors, well, before I move on to unit vectors, right? Especially from a form 4s, let me hear from Soraya and let me hear from Caitlin. You know, looking at this cheat sheet, how do you all feel about the topic of vectors? So let's deal with these two new things real quick. They're real easy. A unit vector, I mean, oh gosh, I don't even know how to, I don't even know why. But essentially, it's just a different way of writing a vector, right? We have, you know, like a vector OP, which is 2, 5, right? You know, the 2 is the X, and the 5 is the Y. Well, now they're gonna call X I, and they're gonna call Y J. I and J. And the reason why is this, right? How many I's do you have? How many J's do you have? Because I, you can see I has 1 on the X and 0 on the Y. So I is this one over here. Just this one unit, right? That is I. 1 unit on the X and 0 on the Y. It doesn't go up or down. You can see J here is 1 unit on the Y but 0 on the X. So it's going up 1 unit on the Y, but it doesn't go side to side at all. 0 units on the X, right? So we call these two the unit vectors I and J. And essentially we can express any vector like a unit vector. So if I take this vector P, for example, 2, 5, we can ask ourselves, well, how many I's does P have? And P has 2 I's. Right? How many J's does P have? P have 5 J's. Right? So this here is writing it in the form of a unit vector. And that's all that there is to it. That is pretty much all. And they might ask you something like, add the unit vectors, and you could probably write down this, but I'll write it just now. I wouldn't do it yet, right? But essentially, that's all that it is. You take the x value and you put it in front of I. You take the y value, you put it in front of j, and you're good to go. That's pretty much it. That is all that it is. But then they might probably ask you, well, all right, find, right? Find OP plus OQ, right? And you could come now and you could go, well, OP is 2I plus 5J, right? And OQ plus OQ is 8I plus 4J, right? And then you just add the i's. So that'll be 10I plus 9J. So you add your i's, you add your j, and so it's just, all we did here was vector algebra, you know. When you added the i's, all we did there was add the 2 and the 8. We added the x's. Yeah? And when we add the j's, all we really did was add the 5 and the 4. We added the y's. So it's pretty much the same thing as vector algebra, just in a different way. Just in a slightly different way. Right? So this here is unit vectors, right? And see if you could give unit vectors a quick write down. I'll wait until hear 4 done it. Last one, collinear points. Now collinear points, you're gonna want to remember your parallel vectors thing. The parallel vectors thing is gonna help us here. Now what collinear points are about is they say that we have 3 points. We have a point Q, we have a point P, and we have a point R. And of course, we could take 2 points and we could draw a line or a vector. So that is QP, the vector. We could also take PR and we could draw a line here, and that is a vector. Right? So we had the vector PR, we had the vector QP. The question becomes, hey, are all 3 points on the same straight line? Is all of this one continuous vector? Are all of the 3 points on the same line? I mean, you can't really tell by looking at the graph, because QP could be so, and then PR could be a little bit so, you know, and it's our next vector. But they're looking, you know, so you can't really tell. I mean, look at them. Do they look like they're in a straight line? Do they look like it? Maybe PR looking a little bit so, and QP looking a little bit so, you know, I don't know, right? So how can we prove if the 3 points are on the same line? These are called collinear points. Collinear points is proven if these 3 points are on the same line, right? So prove that the points P, Q, and R are on the same line and therefore collinear. Now, let's just say if I have this here, QP, just not, I need to use QP, and let's just say this is the vector PR, right? Let me ask you all a question. What do you think it would mean if these 3 points are on the same line? What would you say about these 2 vectors here? What would that mean about those 2 vectors? You're close. They're not, remember, they're not particularly equal, because remember, equal vector would be, you know, 5, 7, and then 5, 7. That means that these guys have the same length. They might be in different spaces, but this one going 5, 7, and this one over here going 5, 7. So they equal, and if they equal, then they will be parallel, wouldn't they? Yeah. And if they're parallel, what does that mean? That means that they are going in the same direction. Yes, they're going in the same direction. I was feeling like Homer Simpson there for a second. What?
Well, my button wasn't coming when I was trying to say that it was frustrating.
All right. Yes. Use the mic button as an excuse. No problem. Right? Yes. Technology fails us. So yeah. So if these guys are on the same line, then they would be going in the same direction. And what do we know about guys that are going in the same direction? Vectors that are going in the same direction, we call them parallel. And how do we prove if two vectors are parallel? Well, if one is a scalar quantity of the other. If one vector is a scalar quantity of the other, then they are parallel. That means they're going in the same direction. Not necessarily equal. Equal means that they're going in the same direction and they have the same length as well. The modulus is the same length. And that is how we could form a parallelogram. Same direction, same length. Right? So equal is not particularly the same as having the same direction. Right? But if we could prove that these two have the same direction, right? Well, then we could prove that they are parallel, right? And if they're parallel, but guess what? This point P is on both of the vectors. It's on QP and is on PR, right? So if it is that we could prove that this is parallel to this, and that means that they're going in the same direction, we could also show that, well, it's impossible for them to be parallel because they share a common point. So because we prove it to be parallel, but they share a common point, means that they're not actually parallel, they're actually on the same line. So in other words, in order to prove that these 3 points are collinear, we take this vector and we prove it to be a scalar multiple of this one. And if they both are scalar multiples of each other, well then we'll prove them to be collinear because the point P is on both of them. So they can't be parallel because parallel is separate. Yeah? Parallel don't meet. The only way that you could have two lines that are parallel but they sharing a point, they sharing the same point, is if it's the same line. Yeah? So I am going to let you guys do this right now. Right? I want you to take the vector QP and show that it is a scalar quantity of the vector PR, right? Or you can even show, QP being in the same direction of PR, or you can even show QP having the same direction as QR. So you could actually show that bigger one, the Q to R, right? And if you could show that QP has the same direction as QR, where P lies on QR, so it have many different ways to do it. If you could prove that one of the vectors is a scalar multiple of the other, which is the same procedure as proving that they're parallel. So if you could prove that they quote-unquote parallel, well then you're technically showing that they are collinear. So we can see here, if we look at it there, this point here is on 5, and this point, well actually, yeah, it is on 5, right? Because this is 4, the middle here will be 5, and there's 6, and we are told that is on 5, right? And then this point here is on 3. We're told that is on 3. You understand? If we look at the vector QP, how many x spaces does it go? It goes, well, 6 to 4, that is 2, right? And then it goes 4, and then it goes 6, and then it goes 8, and you see in that sculpture?
Yeah.
Right? So in terms of horizontal x, the x's, it actually goes 8 spaces, because we can see here each one of these big squares is 2, right? 2, 4, 6, right? So it goes 8 spaces horizontal. And how much does it go down? Well, we can see here it on 5, it goes 4 and then 3. So it goes 2 down. You see in that, Scotia?
Yeah.
Right? And now let's check PR. Now PR, well, we know P here is on 3 and R is on 2, right? So therefore it goes down from 3 to 2. That Y value there is 1, right? And the X value, we can see how much does it go across? 1, 2. It goes horizontal 2 spaces. So 2, 1 is PR, right? So we have here QP is the vector 8, 2, and PR is the vector 2, 1. So we could see that QP is, if I was to take PR and I multiply it by how much? 2. And this is -2 because it's moving down 2 spaces, right? And this here, the other mistake here is this is 2, 4 because it's 2 units per square. So this is 2, 4. So this actually moves horizontal 4. And then it moves vertical -1. Right? So my bad. Sorry about that. So this here is actually 8, -2, and this is 4, -1. Shazay and Scotia, you all understand how I came up with these vectors?
Yeah.
All right. So you can see here that obviously QP is 8, -2, and PR is 4, -1. So if I take 2 and multiply it by PR, right? So therefore QP is 2 multiplied by 4, -1, and that is 4 2s are 8, -2. So yes, they are scalar multiples of each other. So therefore A is equal to KB, hence they are collinear. Right? And look how easy that was. You know that you could have used position vectors to find QP, right? Because what we did was we used the Q, and I'll just do this quick, and you don't have to write it down, right? Because we're gonna do a question like it now. But we just worked out QP by the graph. But what if the graph wasn't drawn to scale, right? Well, we could have easily seen it because we have the coordinates here. So we could have worked out from those coordinates here, well, you know, -6 to 2, that is 8 degrees, 8 units, and then 5 going down to 3, that is -2 units. So you can definitely work out the vector just by looking at the points. Yeah, you can work the vector out. Or you could have go this route, OQ, then you have QP, and then you have OP, right? So I could have say OQ plus QP will give me OP. OQ plus QP gives me OP. And therefore find QP by just taking the OP and minus, and you take this and fling it across OQ. Right? So OP is 2, 3, that is the position vector, minus OQ is negative 6, 5. And look at what we end up getting. 2 minus minus 6 is positive 8. 3 minus 5 is negative 2. So we could have used the position vectors to work out what OQ is. We could have just looked at the points and worked out what OQ is. Or we could have looked at the graph like what we did. Right? So that's it, and we have the cheat sheet here, and if anybody wants to screenshot the cheat sheet, that is cool. We do have a couple of things to add to the cheat sheet though, so let's add unit vectors. So a unit vector is, if I have the vector AB, which is 2, 5, then that would be 2i plus 5g. That is all, right? And you have to know. So if they give you a vector 2i plus 5g, and they tell you to find the modulus of that vector, right? You're supposed to know, well, that 2 is just the x value, and that 5 is just the y value. You're supposed to know that, because sometimes they will give you the vector in the ij form, and you're supposed to know, hey, those numbers in front of ij, that is just x and y, right? So you have unit vectors, and then we have collinear. And collinear doesn't have anything special to write. I just gonna say how I gonna prove that they're parallel. So A is equal to KB. Once you prove that they're parallel, and you also show that they have a common point. So prove that they're parallel, and then they have a common point, and that means that they'll be collinear. Nice. So that is the cheat sheet. If you want, you could take a screenshot of it. But what I have here are some questions from the textbook. These are just some basic textbook questions that we're going to be tackling today, right? And then we also have some Csec questions here that we'll be tackling next class, and you'll have to do these for homework. I believe I did give you 2 Csec questions to do for homework last class, right? Did I?
Yeah.
All right, then you all get through them? Okay, right? So let's try some of these easier questions first, right? Given the points, we have 2 points here, and I guess this is point B, right? They don't have B there, but I'm going to guess that is point B. Right? So A is negative 5, 4, and B is negative 7, negative 3. Determine AB. Right? So I can have, let me just say, I could just do a sketch. Right? And well, I've seen some negatives there. I've seen a lot of negatives there, so I'll just sketch it like this. Right? And I'll say that A is negative 5. 1, 2, 3, 4, 5. And then 4. 1, 2, 3, 4. So that is A. And then B is negative 7. So negative 5, 6, 7. And then negative 3. 1, 2, 3. So negative 7, negative 3. And this here is B. And A is negative 5, 4. And they tell you to find the vector AB. What is the vector AB? Anybody? How can I find what is the vector AB? What do you think? What are some of the things that you're thinking first that I could do?
Yeah.
What do you mean you add? Just add them just so? And that's a good thing, because you want to find out. I know that's a great thing. I have many different ways that we can do this, but you're talking sense there. What you're talking about is the translation. right? Where what vector will translate point A to point B. So that is one way we could definitely work it out, right? Because you have point A plus some vector, and that will give me point B. Yeah? So therefore, point A being -5, 4, plus some vector is going to give me -7, -3. Right? And so we could kind of see here, right, that that I could just throw that across. So therefore xy is equal to -7, -3, and it's a plus on this side, so on this side it will become a minus -5 and 4. That is one way, right? So we could say, you know, -7 minus -5, that's -7 plus 5, which is -2. And then -3 minus 4 is -7. So we have here -2, -7 being the vector that translates A to B. So that is one way to work it out. Another way to work it out is I have a sketch here. I could just literally look at the graph. I say, well, this is -5, right? So how many horizontal spaces do I go? Well, this is -5, this is -7. So that means that I'm moving -1, -2, right? -1, -2 horizontal spaces. So I could easily see, well, all right, I'm moving -2 horizontal spaces. How many vertical spaces? Well, I see I am +4 here, and I had to go down to -3. So that's 4 and 3 is 7. 1, 2, 3, 4, 5, 6, 7. So that's -7 because I'm going down. Right? So I have -2, -7, and that gives me the vector A, B. So we can see here that I have different ways that I can work this out, right? Another way, one way was to use the translation method. Another way was to just look at the graph and look at your points, right? You should be able to make out what the vector is just by looking at your points. And another way, if it is you like to bust through the wall instead of going through the door, is you could actually work out your position vectors, OA. OA plus AB will give me OB. That is a triangle law. Right? So OA plus AB gives me OB. So I know I want AB. That's the one I want. So I'll just take OA and fling it across. So therefore AB is equal to OB minus OA, which is OB is -7, -3, minus OA, which is -5, +4, and look, I end up with the same -2, -7. Yeah, and it didn't take, either way, it didn't take me long. Of course, just looking at it was the quickest way, but sometimes you wouldn't always be able to look at it, right? Now, we see here that we use 3 different ways to work out what the vector is, right? 3 different ways. The translation vector as a translation here, right? We used position vectors over here, and we just use we eyes and some common sense over here. And now it's just simply to work out the modulus of AB, which is the square root of -2 squared plus -7 squared, which is the square root of 2 2s of 4 plus 7 7s of 49, which is the square root of 54. 53. Yeah, 53. What is the square root of 53? 7.2. Wait, let me just check that. 49, because all you do ever correctly, plus 4 is 53, yes. So the square root of 53 is 7.2, so that is 7.2 units long. So you can see here we did a lot of stuff. Write this down, and I want you guys to do these 2 questions right now. And listen, you're only gonna have 2 minutes to do this one, and you're gonna have another 2 minutes to do this one. So that's 4 minutes. Write this down. These 2 questions, 4 minutes. All right. So I have A, B. A is 5, 7, and B is 6, 3. 6, -3. So let me draw a sketch. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So A is about here. A, 5, 7. And then B is 6. 1, 2, 3, 4, 5, 6. -3. 1, 2, 3. So B is down here. And so we have the vector A, B going like this. Right? So the vector A, B, we can literally just look at it on the graph and see how much does it go horizontal. Well, the x-axis here is 5 and the x value here is 6. So it goes 1 spaces this way, positive. So we could tell that is a positive 1 up here, right? So it's going in this direction from 5 to 6, so that's a positive change. But then now let's look at the horizontal the vertical direction. It goes from 7, so 7 to -3. So that is 7, 6, 5, 4, 3, 2, 1, 0. Alright, so that's 1, 2, 3, 4, 5, 6, 7, 1, 2, 8, 9, 10. 1, 2, 3, -3, right? So we see here that this 7 plus this 3 down gives us 10 vertical. So that means -10 on the vertical, right? So we have here AB being a positive 1 and a -10 down, and therefore the modulus of AB is going to be equal to the square root of 1 squared plus 10, well, -10 squared, which is the square root of 1 plus 100, which is the square root of 101, which is square root of 101, 10.049, 10.05, let's just put that. Right? School Shushes, you all got anything close to this? Alright.
I didn't finish.
You didn't get to finish, you were still writing the thing on.
Yeah.
Alright, but were you on this track?
Kind of.
Would you like time to write this down?
Yeah, it's done.
Alright, okay. And I hope that my Form 4s have written it down as well. Alright, so let's do this number 13 there. So number 13, given position vectors. Oh my goodness. Alright, 2 minutes guys, 2 minutes. I'll start by drawing a little sketch. Now position vectors does just basically mean that from the origin the point P is 5, 3. That's all that it means. Right? So 1, 2, 3, 4, 5, 1, 2, 3. That is the point P there. 5, 3. And then I have the point OR. Well, the point R is -9, 6. Wow. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then positive 6. 1, 2, 3, 4, 5, 6. So that there is my point R, which is -9, 6. Now, yes, you could have used position vectors to work this out because they want to know the distance from P to R. And in order to find the distance from P to R, you're gonna have to work out the vector PR. And yeah, you could do the whole position vector thing, and we'll do that after, but you didn't really have to. If it is that you notice that a position vector is just a point, right? Then you could have said, well, okay, if this is 5 on this side, and this is -9 on this side, then the entire distance that is going horizontal would be the 5 plus the 9, right? So 5 plus 9 is 14, so it's going -14 in this direction, right? And how much is it going up? Well, if we look here, so this one was 5, this one was -9. If we look here, this is on 3 and this is on 6, so we can see that it's going up by 3 spaces. So it's going up by 3 spaces there. So we have -14 spaces this way on the x, 3 spaces this way on the y. Is this the vector you guys got for PR?
Yeah.
And once you got this vector for PR, all you need to do is the square root of -14 squared plus 3 squared, which is the square root of 14 squared is 196 plus 3 3s are 9, which is 205. The square root of 205 is square root of 205 is 14.3. You got that?
Yes, sir.
What about you, Shizzy? Anywhere close? Huh? You got it wrong? Why? You had what? -4 and 9 for your vector. How you get -4 and 9? Because you add 5 and -9. Yeah, but why did you just add? Why did you just go about adding? Right? Did what I do there, did it make sense?
Yeah.
Right? You sure it made sense? So why did you add 5 and -9? Remember, if you wanted to do it the translation way, right? You want to find PR, right? So you had to say that, well, the point P is being added by some vector to give me the point R. So the point P, which is 5, 3, is being added to some vector xy to give me R, -9, 6. So you'll see here that I have to know, so it's not a matter of just adding them, it's a matter of knowing the theory, right, Shizzy? Right? Knowing the theory and knowing how to apply it. So I have to throw across the P, so it'll become R minus P. So xy is going to be R minus P, which is -9 minus 5 is -14, and 6 minus 3 is +3. You understand, Shizzy? Now, there is a third way we could have done this, and that is using position vectors. Right? Now, you can see that I just basically used just a little bit of reasoning. Right? So you didn't have to do the translation way, and you didn't have to do the position vector way either. But let's look at the position vector. We could see here that we want to find PR, right? Well, we could say that in the triangle law, OP, this is O, right? So OP plus PR will give us OR. OP plus PR gives us OR. So we have OP plus PR gives us OR. What do we want to find? We want to find PR. We have OP, we have OR. So we want to find PR. So PR is going to be OR. We fling across the OP, so it'll be minus OP. Right? And therefore OR is what? Negative 9.6 minus OP, which is 5.3. And we end up getting the same thing, negative 14.3. You understand where you did wrong, Shazay?
Yes.
You can't just go and add in any vectors you want. You know, you can't just go adding points. You had to think about it logically and with some reason. Understand?
Yes, sir.
Alright. Don't worry. This is what is get everybody tied up with vectors here, right? This looks like the same questions. So yeah, I guess we're not doing this. Yeah, I think those are the same questions. Right. So this here is a nice one, and this kind of sums up a lot of the stuff that we have been doing in the past couple of classes here. Let's see if you guys could tackle number 4. Alright, time is up. Let's see how you guys fared with this one. Now, I will always draw a sketch for a vectors question because it has helped you see things a lot easier, right? So the vector OA, the position vector OA is negative 6, 5. I am reading nothing else yet. 1, 2, 3, 4, 5. Negative 6, positive 5. 1, 2, 3, 4, 5. So that is the vector A. Right? That is the point A. Negative 6, 5. Right? So the vector OA is the same as the point, you could see. Right? And then we have OC, which is negative 2, 1. So 1, 2, and then 1. So that is C over here. Negative 2, 1, 2, and then positive 1. So that is C, which is negative 2, positive 1. Right? Now I can see here my sketch. In this case, the sketch is probably not going to help me very much, right? So let's just see, because the sketch is kind of, you know, crazy, right? So this OC is going like this, and this OA is going like this, right? And we can see here that the pulling is like the horses, 2 horses pulling a cart in 2 different directions, where O is the cart. They're not following each other, right? Now they say here that it's 2 sides of a parallelogram. So this kind of messing me up, this diagram. So let me just draw this a little better. I have OA, right, which is negative 6, 5. And then I have OC, which is here. I'll just put the O a little bit lower. O. And then I have OC, which is here, which is negative 2, 1. Right? So I just kind of expanded the diagram just to see. And they say that this makes a parallelogram AOABC. So obviously I have to make a parallelogram, and so what I'll do is I'll make a side as parallel, and should I do this in a different ink? I'll make a side that's parallel to OA, right? And this side will also be negative 6, 5. Because it's parallel and equal. And then I'll make a side parallel to OC. This side will be negative 2, 1, because it's parallel to OC, so it's parallel and equal. So that gives me my parallelogram, and that gives me the point B over here. And now we can see here that now I have this position vector, which is the resultant. OB. Nice. So Shazay, Scotia, you guys understand this stuff so far?
Yes.
Yes.
All right. So so I see my graph wasn't really helping me because it was too chinksy. So I have this here that helping me a little bit instead. Right? And you see how I approached it, Shazay. I didn't just jump to the conclusion of just starting to add like mad all over the place. No. You know, you take it piece by piece and you draw it out. Right? So now the resultant, I want OB. So OB, I can't really count. And the graph doesn't really help me in this case to count and such. So I'll have to do the parallelogram law. The parallelogram law, I could see here that OB from here to here, I could get to OB if I went OC plus CB. So OB is equal to OC plus CB. And you can see there that that's correct. The C's cancel or end up with OB, right? So now I could see that OC is negative 2, 1 plus CB is the same as OA, so negative 6, 5. So it's not, so yeah, I did just add them, but it's not just about, well, just add anything. No, you have to reason it out into what you're adding. And in what order are you adding in, right? So negative 2 plus negative 6 is negative 8. And 1 plus 5 is 6. So we have OB. And we could tell OB negative 8 because it's quite long in this direction, right? And then we have 6. It actually, we could tell that the B is higher than the A. And it's higher by 1, yeah? So we could tell here that OB, we could tell that the point B is negative 8, 6. And OB is negative 8, 6. We use the parallelogram law here. Scotia, Shazay, how you felt about this one? Oh, lovely, beautiful, beautiful. All right, and of course, the magnitude OB is just the magnitude of OB is just the square root of negative 8 squared plus 6 squared. And what you guys got for this? What's the answer here? $10 is the answer, right? And then they want the acute angle between OB. So OB and the x-axis. So if this is OB, they want the x-axis, this angle here. And OB is negative 8, 6. So what do we know? We know that that angle is the tan inverse of y over x. That you'll get an answer negative 36.86 degrees, but you could just take the 36.86 degrees. That negative there is a whole kind of scene there that you all don't really have to know, but you could just take the 36, and it does look 30-ish in terms of as far as angles go, right? So Scotia, Shazay, you all understand this one? Yeah, let's do this. I'm gonna give you all 5 minutes for this one. Alright, that's about it for you. So let's see here. They actually gave us a diagram. How kind of them, right? I guess they don't want us to do anything drastic. So we see here that the points A, B, and C have coordinates that, and that respectively as shown in the diagram. So we have point A, which is 4, negative 5. Alright, it looked negative 5-ish to me, right? We have the point B, which is 3, 4. And then we have the point C, which we do not know, which is P, Q. and that is the point C that we don't know, respectively, as shown in the diagram above. Write the points A, B, and C as position vectors. So position vectors, remember they gave us points, so therefore OA as a vector would be 4, -5. That is all. That's it. OB, remember the position vectors, position. So you're thinking origin, you're thinking O, right? So OB is 3, 4. And then OC is P, Q. Next, so I have my 3 position vectors here. Hence, calculate the length of the vector AB. Now the vector AB goes from A to B, right? And I don't need to use position vectors because I have the coordinates for A and B, so I can literally work it out. To go from A to B, let's look at the x's. I'm going from 4 to 3, so I'm going back 1. So therefore the x value here is going to be -1. And the y value going to be what? Well, I have to go up a certain amount of spaces here. I see that I have to go up 5 spaces here because this is -5. So this is 5 spaces I had to go up, plus an additional 4 spaces because this is 4. So I could see that I'm going up, so that could be +9, right? So at the end of the day, the vector AB is -1 on the horizontal and +9 on the vertical. That gives us the vector AB. So I did not have to use position vectors to work it out. I could have used common sense to work it out. But the first question A, write the points A, B, and C as position vectors. Second question B, hence calculate the length of. So that means hence means that I have to use what I did before. So I have to use position vectors. All right. So they want me to use position vectors to find the vector AB, right? So what are the position vectors I have? I have OA and I have OB. So I could use the triangle law. I could say that OA plus AB gives me OB. Yeah, the resultant. OB is like the resultant. So OA plus AB gives me OB. So I could start with that. OA plus AB gives me OB. And therefore fling across the OA, because what do I want? I want AB. So AB is OB minus OA. I fling across the OA. So you see, sometimes you can't just be adding them. Sometimes you might have a minus. So AB is equal to OB. OB is 3, 4 minus OA. OA is 4, -5. Right? So what do I get here? 3 minus 4 is -1, and 4 minus -5 is 4 plus 5, which is +9. So look, I used common sense to figure out what it was, but because they have the word hence, means that I had to use position vectors to figure it out. And because they use the word hence, I use position vectors, but I figured it out from before, so I don't know the answer I was supposed to get. Right? Remember, you could have also used a vector as a translation to translate from A to B. You would have worked out with the same kind of thing. Right? So determine the values of P and Q if OACB is a parallelogram. Okay. So I had to make sense of that. If OACB O, A, C, B is a well, it don't look like a parallelogram there because this AC is supposed to be equal to OA, and that certainly don't look equal. But you know what? They tell me is a parallelogram. So I will assume that AC is equal to OB. So if parallelogram, so this is part C, if parallelogram, that means that AC is equal to OB, and that would also mean that this vector here, BC, would be equal to this OA on this side. Alright, so if that's a parallelogram, well, I know all of them things equal up then. Right? So if all of them things equal up, well then, okay, so let me just move this right there. If all of those things equal, then what do we want to find? We want to find, determine the values of P and Q. P and Q is OC, and so OC here, OC, OA, OACB is a parallelogram. OACB is a parallelogram, right? So guess what? Any ideas on how to do this? Because I have a couple of ideas here. But how did you guys, any thoughts, Shizzy or Scotia, on how to do this one? And sorry, yeah, but I'll keep you guys back maybe a little 5 minutes again, right? Sorry about that. Scotia, any idea what to do here?
No.
What about you, Shizzy? Isn't this vector here equal to this vector here because it's a parallelogram? And would you agree?
Yeah.
And this vector OB, that is the vector 3, 4. Would you agree with that?
Yeah.
So that means that this vector here is the vector 3, 4. Would you agree with that?
Yeah.
Right? So therefore, I know the vector is 3, 4, and I know it coming from a point 4, -5, and I know that? Yeah? So if it coming from a point A, it coming from the point A 4, -5, the point A is being translated by the vector 3, 4. Right? So let me call this vector 3, 4 vector B, because it comes from OB, which is 3, 4. Right? So I could just use vectors as a translation. So therefore I could say, well, okay, you know, the vector, the point A plus the vector B is going to give me the point C. Okay? Usually we just have to fling across something, but not in this case. In this case, we have the vector, we have the point A. The point A is 4, -5, plus the vector B, which is 3, 4. And that'll give me the point C, which is PQ. Okay? So therefore, and you see how easy it turned out to be once you realize that it's a parallelogram and what a parallelogram means. And then, of course, you know all of your work from your cheat sheet. So you know what do you have to your disposal? Position vectors, you have vectors as a translation, you have common sense, you have other things, you know. So now we could see here that 4 and 3 is 7, and yes, C does look 7-ish, right? And then I have -5 plus 4, which is -1. So C ends up being the point 7, -1. Notice how I wrote it horizontally, right? Where P is equal to 7 and Q is equal to -1. So this is 7 and this is -1. Right? Now, the next question here, calculate the midpoint of BC. This is actually a coordinate geometry question. Remember the midpoint in coordinate geometry, and this is part D. Midpoint is if I have the midpoint of 2 points, that is I add the x's, x1 plus x2 over 2, and then y1 plus y2 over 2, and that will give me the midpoint of both of those points there, right? So I have the midpoint of B to C. So B being the point 3, 4, and C being the point 7, -1. So I could just plug those into my midpoint formula to get x, the x's, you add the x's, so 3 plus 7 over 2, comma, then you add the y's, 4 plus -1 over 2. 7, 8, 9, 10, so that's 10 over 2, and 4 minus 1 is 3, so 3 over 2. So therefore the midpoint, M, is 5 on the x and 1.5 on the y. And it does look like that. If it is that I have the midpoint here, M, it does look 5-ish here and then 1.5-ish on the x there. Right? So these were some basic, well, not really basic, but you'll realize that the Csec questions only look harder. But look at all of what I did. Apart from this, which was coordinate geometry, which you all should know, right? Everything else was pretty basic and simple. Is the problem with you guys, especially Csec and especially Scotia, is that you all overthink. You have to always remember, what do I know? What do I know? I know this. This is all that I know. So they could never ask you a question that you don't know. Anything that they ask you will be using one or more of these. And look, in this cheat sheet here, this is the entire topic of vectors in one paragraph. And this is how you do a cheat sheet.